All right, we're going to do lesson 3-2. Here we go. 3-2. We're going to do some real-life applicable problems here, which is really good. That means word problems. So, no, but everyone's like, when are we ever going to need this? And then as soon as I'm like, oh, here's a word problem that no, I don't want to do it. It's true. Is that how you spell exponential? Yeah. Exponential and logistic. That is not logs, okay? That's different than logs. We learned that yesterday. Logistic modeling. Do some modeling today. Okay, not that. Mathematical models. Can you imagine? How pretty would they be? Not. All right, here we go. We have a few parts. We're going to do part A. We're going to do growth and decay. Yeah, I'm sure I'm going to get lots of comments. Your vids are trash and stuff like that, and that's all right.
Do you think, like, strangers watch your vids?
Yeah, maybe. I don't know. Because, yeah.
Comment below.
Comments are turned off. Okay, growth and decay. Now, growth and decay is going to be done two different ways. Okay? Number one, here's the first way. Growth and decay is going to be denoted by something called R. And R is going to be the constant percentage rate. Constant means it's not going to change, you know. It's not going to say, oh, it's 2% rate or growth in this time, and then it changes to 2.5. It's not going to do that. It's just going to be 2 the whole time, or 4, whatever it is. So constant percentage rate. And it's a percentage rate. Okay? And then here's the formula for this. And you learned this last year in Algebra 2. P of T, we're talking about population growth mostly. Sometimes we're in a petri dish and bacteria grows and stuff like that. But P of T equals P sub 0, which is your initial amount or your initial population, and then 1 plus R to the T. Do you remember that formula? Yeah. That's annual growth. So there it is. And they tell you here that if R is greater than 0, it's going to be growth. Okay? And if R is greater than 0, then that means that 1 plus R will be greater than 1. So if you have a growth rate of 2%, you're actually getting 102%, right? Because you're getting 100% of the population back plus 2% more. So that's why you have to do as 1 plus the percentage. If R is less than 0, then it's decay. Okay, so if you have 1 plus R inside of there, that's going to be less than 1. So for example, if I have a decline of 2%, that's really like doing 1 plus negative 0.02. It's a little bit different in this book. In Algebra 2, we did 1 plus R and 1 minus R. It's the same thing, okay? Which would be 0.98. And you'd see 0.98 inside of there, which means only 98% of the population is coming back. So that would be a decline, okay? All right, so let's do our first problem. Number 1, we're going to decide whether this is growth or decay. And we're going to find the rate of growth or decay, the R value in both of these problems. Okay, so I have 2 cities. I've got San Jose, which is beautiful. Have you ever been there? San Jose? Gorgeous, up the coast. They have a terrible hockey team, though. No, I haven't done any yet. Number 1? Yeah, so the Sharks. No one likes Sharks. Okay, in the San Jose, it says the population for time would be 898,759 times 1.0064 to the T. Okay, we're going to talk about that in just a minute. Now I'm going to give you another city, the beautiful city of Detroit. Right? The Red Wings. Nobody likes the Red Wings in here. Mr. Becksford did, though. A lot. Yes. A lot of people like the Red Wings, actually. Last year was the first year they didn't make the playoffs in like 25 years. Wow. I know. Yeah, it was awesome. Okay, 1,203,368. And in here is 0.9858 to the T. All right, so let's talk about these. Now, San Jose, you can tell the initial population is just under 900,000, and Detroit, the initial population is 1.2, from whatever they're starting this information from. Which one is growth and which one's decay? San Jose is growth, perfect, and Detroit is decay. Okay, nobody wants to live in Detroit, it's horrible. San Jose, beautiful, people are moving there. We can tell that by looking at the inside, the base of the exponent. Okay, it doesn't matter what the outside stuff is, that's what we're looking for. Now, what is the rate of growth here? The rate of growth is to take 1.0064 and subtract 1 from it. Because inside of there is 1 plus r. So r would be 0.0064. But r is a percentage, so let's make that into a percentage, which would be 0.64%. 0.64. So not quite 1%, but it still has a growth. There's still people, slowly trickling in to the city. Now over here, Detroit, we knew it was decay, 0.9858. So what I like to do to find r is I'm going to go 0.9858, and I'm going to subtract 1 from it. Oopsies. Thank you. 8. And then I get negative 0.0142. So you could say that it is declining at a rate of 1.42%. I don't know if the book just says they make it positive and they say that it's decreasing or decaying at that rate, or if they leave it negative. Either way, it's fine. Okay? All right, the second way, so that was number 1. That was given a rate of increase or finding the rate of increase. The second one is just given a value. The value is going to be something like it doubles every 6 months, bless you. Or half of it's gone after 2 hours, okay? So things like that, instead of a percentage, it's an actual value. So let's do 2 of those. Number 2. It says that I have 100 bacteria in a petri dish. And this is going to double every hour. Whew. Okay? It's going to double every hour. So I'm going to A, write an equation that models this. And then I'm going to B, find out how long will it take for this petri dish to have 350,000 bacteria in it. It's starting at 100. How long is it going to take to get to 350,000 bacteria? All right, so let's start first by making our equation. So here we go. You don't need to worry about 1 plus r here. It tells you the growth rate is 2. It's doubling. So this would be y equals my initial amount times 2 to the x. Okay, so it's not the same as 1 plus r. It's just the growth rate is 2, so 2 goes in. The second part is going to be how long will it take to get 350,000 bacteria. Now that's not x. X is time. Y is the bacteria. So I need to plug in 350,000 and I need to solve. Thank you. Yes. We can solve this algebraically. We're not quite there yet. You might remember how from last year you have to take the log of both sides and solve it that way algebraically. We're not there yet. We're going to graph this, okay? I want to make it a little bit easier, though, by dividing both sides by 100 just to get rid of these huge numbers.
Would you still do that if you were going to solve it algebraically?
Yes, you would. That's how you'd start. Good call. All right, 3,500 equals 2 to the x. And this is how you're going to solve this graphically. You're going to plug this in for, let's say, y1. And you're going to plug that in for y2 on your calculator.
Could you just plug in to the y equals 2x, or
Minus 3?
No, minus 3,500.
Minus it from where? Oh, and then set it equal to 0? Yeah, you can do that. I kind of like this way a little bit better because I know what, like I need 3,500. So I'm going to go with 3,500 and for y1, y2 is 2 to the x. And now I got to fix my window, okay? So that's the hard part, right? I got to think, well, my y has to be more than 3,500 because I'm going to have this horizontal line at 3,500. My x, I don't know how long it's going to take. What do you guess it's going to be? 20? 50? Yeah, I don't know. Just try something. And then y would be 0 to, I'd say 4,000. I want to make sure that I'm up high enough. So there's my y is 4,000, and here comes my exponential graph. Perfect. It's a little too much, but it doesn't matter, right? So that, and then you get this, and you want to find out how long it's going to take. You want to find the intersection. So second trace, which is calculate number 5, hit enter 3 times, and you get that it's going to be about 11.8 hours. Wow, that seems fast, doesn't it? You started with 100 of them. They're doubling every hour. That's super fast. See how fast exponential growth is? All right, let's do number 3. Where's this 4? 3. Okay, let's do a half-life problem. So let's say we have radioactive decay. Radioactive. All right, sorry. I did that yesterday, huh?
Yes.
And nobody laughed then. So why did I do it again? You got to know your audience.
I think we've heard that one before.
Have you? Radioactive, well, you've heard them all pretty much. Radioactive decay, half-life. Okay, let me give you the old half-life formula. Maybe you did this in chemistry? Yep. And in algebra 2, regular algebra 2, we did it too. All right, y equals a sub 0. That's your initial amount. The decay factor is 1/2. This is going to be to the t, but then we have to divide by whatever the half-life is. Don't get those mixed up. People get those mixed up all the time. It's still to the exponent, to the t, but you have to divide it by the half-life of the substance, okay? I'll show you why in just a minute. All right, so here we go. Let's say that you decide to take some medicine, good medicine. You're not taking drugs, okay? You decide to take some medicine, and you take 200 milligrams of whatever, Advil or who knows, okay? And it says here that it has a half-life, of, I don't know, 2 hours, right? You take some medicine, it's pretty strong in your body at first, and then it starts to like just go, and then you need more later on, right? You have a headache again. Okay, has a half-life of 2 hours. The question is, when will there be 25 milligrams left in your system? Maybe you have to take a drug test for work, and you're like, when's this going to be out of my system? You know what I'm saying? Okay, anyways, here we go. Nope. Y equals, it's what? That's okay. People like to have fun. Y equals 200, 1/2 to the, you could say x or t, it doesn't matter, x over 2. Now, do you see why we divide by 2? Like if I said, how much is left after 4 hours, and you plug in to the 4th, that's not right. Because it's the half is every 2 hours. If it's every 1 hour, yeah, then it's 4 over 1 is just to the 4th. But this is every 2 hours, so you have to divide whatever you're plugging in by 2 to get the right amount. Now, the question is, when will you have 25 milligrams left? So we're going to plug 25 in for y, and we're going to graph this, okay? We're going to solve by graphing. Later on in the chapter, we will solve this algebraically, so don't feel like, oh, I wish I could solve this algebraically. You're right, we'll get there. It'll be okay.
This will always be on the calc portion, though, right?
Oh, yeah, for sure. So you can check your answer, but I will, yeah. If it says algebraically, you'll have to show work. Okay, you could divide by 200 if you want to. I'm not going to. I'm just going to leave it as is, and I'm going to plug in y1 is 25, and y2 is 200 times 0.5 to the x. Let me show you what that looks like. I just did 0.5. You could do 1/2 also. And I got to change the window. I don't know how long it's going to take. Let's just leave it at 50 for now. But I do know that my y maximum is going to be no more than 200, because 200 is the most that you're going to have in your system at a time. And then there's 200. Oh, wow. That is like way off, huh? So maybe your window is better at like 20. What am I at? Oh, we're okay. Yeah. Okay, so let's calculate the intersect. And it's going to take, did you guys know that already? Did anyone do this in their head? Yeah? That's good. I wasn't even thinking. I was just doing. Do you ever do that? X is going to be, did I do this right? No, I didn't. I didn't plug it in right. How come no one told me that? It's your guys' fault. I went to the X. It's X over 2. Whoopsies. I thought something was wrong. Yeah?
It's not supposed to be x over 2?
There. No, it is supposed to be X over 2.
X over 2.
X over 2. I did it to the X. So I was getting the wrong answer. I didn't think it was going to be 3. That wouldn't be right. Yeah. I totally forgot. All right, X is 6. 6 what? 6 hours. 6 hours. Think about it. You have 200 milligrams. After 2 hours goes by, you're going to have 400. 100. I was doubling. Wow, I should just move on. And then after another 2 hours, you're down to 50. And then another 2 hours, you're down to 25. So it took you 6 hours.
So if we, that's like technically solving it algebraically?
It is. No, that's not solving it algebraically. Okay, let's look at the next part. What time are we at? We're on Disaster Drill 2017, so we're out at 1:10. What? Okay, the last part. This is why I don't record in here. All right, regression. My iPad was dead. Yeah, no. I talk too much. It's my fault. I get it. All right, regression. You're going to have a couple of different types of regression in here. That's true. We're going to have exponential regression, and we're going to have logistic. Okay? Logistic's that really ugly one. Don't think that's log. Don't think it's natural log. So what you're going to do is you're going to plug in, you're going to go to stat, and you're going to plug in L1 and L2. And then you're going to follow what they want you to do. If they want exponential, you give them exponential. If they want logistic, give them logistic. So let me show you. I already have some data points in here, okay? If I hit zoom 9, that's what it looks like. Okay, that's interesting. It's not linear. Oh, that's funny. Okay, I'm going to go to stat calc, and I'm going to scroll down to some things I've never used before. So this is exciting for you. There's ln, that's natural log. We're going to do that another time. There's exponential. You're going to use that one, exp. Power, don't ever use that. And then there's logistic. Now logistic, you might think your calculator's broken. Okay, it takes a little while. Sometimes the more data points, it takes a long time. Look how gross that is. You see that? And then you would have to plug everything in to write your logistic function. 98.8, we know that's going to be the upper bound, the asymptote up above. And then you plug in 1 plus 1.1 e to the negative 0.2766x. Okay, that's going to be the logistic function. If they ask for logistic, give them that. They ask for exponential, you will. The thing with logistic is it doesn't give you an r or an r squared. So you would need to go to y equals and actually plug it in and see how good it is in your graph. Okay?
The rest of it's not solved?
No, I did. I finished it.
What about
Oh, it tells you A, like B, C, D. Yeah. Yep. It's the equation, and it tells you like where you're at. Here's my logistic graph if you are interested. It's pretty close. Goes through a lot of those points. All right, have a good one.